quiet dark of space, not everything is still. Galaxies, those majestic spirals and glowing clusters we see in telescope images, are not isolated islands. They move, shift, and sometimes devour. Tonight, we travel to a corner of the universe where a galaxy is not just growing, it is feeding. A vast collection of stars and gas being pulled in, digested, and reshaped. And it is not the only one. Across the cosmos, galaxies are swallowing their neighbors, consuming them across millions of years in silent collisions and gravitational dances. These acts of cosmic cannibalism are not rare, they are essential. This is the hidden story of how galaxies evolve, grow, and sometimes even survive. The stars above your head tell this tale. Some were born in galaxies long since consumed by our own. Others live in streams of stars, the remnants of galactic meals from billions of years ago. The universe you see is not static. It hungers, it feeds, it transforms. As you drift towards sleep tonight, imagine the slow cosmic dance happening far above. Galaxies approaching one another over billions of years. Stars being pulled from their homes into new orbits. Gas clouds colliding and birthing new stars. This is not destruction. This is creation through consumption. This is how the universe builds its most magnificent structures, one galaxy at a time. Throughout our journey tonight, we will witness galaxies in various stages of their cosmic feast. Some are just beginning their approach, their gravitational fields barely touching. Others are deep in the process of merging, their shapes distorted and stretched. And some have completed their meals, now digesting the stars and gas they have consumed, forming new structures and patterns that will last for billions of years. We humans, living our brief lives on this small planet, rarely perceive these epic changes, but they are happening all around us, in slow motion by our standards, but in a continuous flow on the cosmic scale. The universe is constantly renewing itself through these galactic feasts, building larger structures from smaller ones, creating new opportunities for stars and planets, and perhaps even life itself to emerge. So settle in as we explore this silent cosmic feast, a tale of hunger and growth, written across the night sky in stars and gas and dark matter. A tale that continues even now, as you listen to these words and gaze upward at the seemingly peaceful night sky. Imagine standing on a beach, watching as a large wave slowly absorbs a smaller one. The process is gradual, almost gentle, yet ultimately transformative. This is galactic cannibalism. It is the process by which one galaxy, typically larger, consumes another, typically smaller. The term might sound violent, conjuring images of explosive collisions and celestial destruction. But in reality, it is more like a slow, gravitational dance that unfolds over billions of years. When astronomers first pointed their telescopes at distant galaxies in the early 20th century, they noticed something curious. Some galaxies had strange shapes, unusual tails of stars, or odd rings and shells of light surrounding them. These peculiar features didn't fit into the neat categories of spiral, elliptical, or irregular galaxies that astronomers had established. Something else was happening. By the 1970s, computer simulations began to suggest an answer. These distorted shapes were the result of galaxies interacting with one another through their gravitational fields, sometimes passing close to each other, sometimes merging completely. The evidence was written in light across the cosmos, visible to anyone with a powerful enough telescope and the knowledge to interpret what they were seeing. Galactic cannibalism begins long before two galaxies physically touch. The process starts when they are still millions of light years apart. Their enormous gravitational fields reach out across the void, invisibly tugging at stars and gas clouds. As they draw closer over millions or billions of years, these gravitational forces grow stronger. The smaller galaxy begins to distort first, its stars feeling the pull of a new gravitational center. Stars at the edges of the smaller galaxy begin to be drawn away, forming long tails or streams, that stretch between the two galaxies. Gas clouds are compressed, sometimes triggering bursts of new star formation that shine bright blue against the darkness. The larger galaxy feels these effects too, though to a lesser degree, its shape also beginning to change in response to its approaching meal. As the galaxies continue their approach, their outer regions begin to intermingle. Stars that once belonged firmly to one galaxy now find themselves caught between two gravitational centers, their orbits becoming chaotic and unpredictable. Some stars may be flung out into intergalactic space, destined to wander alone between galaxies. Others will be captured by the larger galaxy, becoming new members of its stellar population. The cores of the two galaxies, containing their densest concentrations of stars and often supermassive black holes, continue to move toward each other. Unlike the outer regions, which might stretch and disperse, these dense cores maintain their integrity longer, orbiting each other in an ever-tightening spiral. Eventually, even these cores merge, their black holes potentially forming a binary system before they too combine in an event that sends gravitational waves rippling through the fabric of space-time. Throughout this process, which can take billions of years to complete, the galaxies are changing. It is not a simple case of the larger galaxy remaining unchanged while it absorbs the smaller one. Both are transformed by the encounter, though the smaller galaxy typically loses its distinct identity, while the larger one incorporates the new material into its existing structure. The key to understanding galactic cannibalism is recognizing that it is not a violent collision in the way we might think of two cars crashing together. Space is mostly empty. Even in the densest parts of galaxies, stars are separated by trillions of kilometers. When galaxies merge, individual stars almost never collide with one another. Instead, it is the gravitational interactions that cause the dramatic transformations we observe. This emptiness means that galactic cannibalism is more like two clouds passing through each other, their particles rarely making direct contact, but their overall structures being dramatically affected by the passage. The stars respond to the changing gravitational field, their orbits shifting and adapting to the new reality of two galactic centers becoming one. Astronomers can identify galaxies in various stages of cannibalism by looking for specific signs. Tidal tails, those long streams of stars stretching away from galactic centers, are one telltale sign. Shells of stars arranged in concentric arcs around a galaxy suggest that it has recently absorbed a smaller companion. Rings of new star formation can indicate where gas clouds from two galaxies have collided, compressing the gas and triggering the birth of new stars. Even the internal structure of a galaxy can tell the story of past meals. When astronomers study the motions of stars within galaxies, they sometimes find groups moving together in ways that don't match the overall rotation or structure of the galaxy. These are likely the remnants of consumed galaxies, their stars still moving together, even after being absorbed into their new home. Galactic cannibalism shapes the universe we see today. The largest galaxies in the universe, enormous elliptical galaxies containing trillions of stars, are thought to have formed primarily through series of galactic mergers, each one growing larger by consuming its neighbors over cosmic time. Without this process, the universe would look very different, populated only by smaller galaxies without the diversity of forms we observe. Far from being a cosmic anomaly, galactic cannibalism appears to be a fundamental aspect of galactic evolution. It is how galaxies grow, how they change form, and how they build up the diversity of stellar populations we observe within them. In a universe where everything is in motion, where gravity pulls everything toward everything else, galaxies meeting and merging is not just common, it is inevitable. So when we look out at the night sky, we are not seeing a static, unchanging tableau of stars and galaxies. We are seeing a moment in a long, slow process of cosmic consumption and growth. The light from distant galaxies brings us images of celestial bodies in various stages of this cosmic dance, some approaching their partners, some in the midst of merging, and some bearing the scars of past encounters. This is not a story of destruction, but of transformation. No star is destroyed in these mergers, though many find new orbits and new galactic homes. Gas clouds collide and compress, triggering the birth of new stars that would not otherwise exist. Black holes merge, potentially sending out gravitational waves that ripple through the fabric of space itself. In the cosmic ecosystem, galactic cannibalism is not an ending, but a continuation, a way for the universe to build ever more complex structures from simpler ones. When we gaze up at the band of light stretching across our night sky, the river of stars we call the Milky Way, we are looking at a cosmic predator. Our home galaxy, this collection of hundreds of billions of stars, is not an innocent bystander in the drama of galactic cannibalism. It is an active participant, a consumer of smaller galaxies, and the evidence of its past meals surrounds us on all sides. The realization that our Milky Way has been devouring other galaxies throughout its history is relatively recent. For most of human history, we did not even recognize that we lived in a galaxy, let alone understand that it had grown by consuming others. But the evidence has been mounting, and today astronomers can point to multiple lines of proof that our galactic home is a cannibal. The first major breakthrough came in 1994, when astronomers discovered the Sagittarius dwarf spheroidal galaxy. This small galaxy is currently being torn apart by the gravitational forces of the Milky Way. Located on the opposite side of our galaxy from Earth, it was difficult to detect because it lies behind the dense star fields and dust clouds of the Milky Way's center. But once found, it provided the first direct evidence that our galaxy was actively consuming a smaller neighbor. The Sagittarius dwarf is now stretched into a long stream that wraps around the Milky Way multiple times. Its stars are being pulled away from its core and incorporated into our galaxy's halo. In a few 100 million years, it will cease to exist as a distinct entity, its stars fully absorbed into the Milky Way. We are witnessing galactic cannibalism in action, not in some distant corner of the universe, but right here in our cosmic backyard. But the Sagittarius dwarf is not the Milky Way's first meal, nor will it be its last. As astronomical techniques have improved, scientists have discovered more and more evidence of past galactic feasts. One of the most powerful tools in this investigation has been the European Space Agency's Gaia spacecraft, which has been mapping the positions and motions of over 1 billion stars in our galaxy with unprecedented precision. Gaia's data has revealed something remarkable about the stars in our galaxy. Not all of them are moving in the smooth, orderly patterns we would expect if the Milky Way had formed in isolation. Instead, there are distinct groups of stars that share similar orbits and chemical compositions, yet differ from the majority of stars around them. These groups are the remnants of past galactic meals, the digested remains of smaller galaxies consumed by the Milky Way billions of years ago. One of the largest and most significant of these past meals has been dubbed Gaia Enceladus, or sometimes the Gaia sausage, due to the sausage-like shape its stars make in velocity space. Approximately 10 billion years ago, a dwarf galaxy containing roughly 500 million stars collided with our young Milky Way. The merger helped shape our galaxy's thick disk and inner halo, depositing stars with different chemical compositions and orbital characteristics than those that formed within the Milky Way itself. The discovery of Gaia Enceladus was just the beginning. As astronomers have continued to analyze the Gaia data, they have identified more and more of these galactic fossils. There's the Helmi stream, another group of stars that once belonged to a small galaxy consumed by the Milky Way about 12 billion years ago. There's Sequoia, Tamnos, and others, each representing a once distinct galaxy that has now become part of our own. These discoveries have forced astronomers to reconsider the history of our galaxy. Rather than forming in isolation and evolving smoothly over time, the Milky Way has experienced a series of mergers and acquisitions, each one adding new stars, gas, and dark matter to its growing bulk. Our galaxy's history is written not just in the ages and compositions of its stars, but in their motions, which preserve the memory of their origins long after their parent galaxies have ceased to exist. Perhaps the most visible evidence of the Milky Way's cannibalistic tendencies lies in its halo, the sparse region of stars that surrounds the main disk. Unlike the disk, which rotates in an orderly fashion, the halo contains stars moving in all directions. Many of these stars are organized into streams, long ribbons of stars that share similar orbits and compositions. These streams are the torn remains of globular clusters and dwarf galaxies that have been disrupted by the Milky Way's gravitational forces. Astronomers have identified dozens of these stellar streams weaving through the Milky Way's halo. With names like the Orphan Stream, the GD1 Stream, and the Monoceros Ring, each represents a different chapter in our galaxy's history of consumption. Some are the remains of globular clusters, dense collections of stars that were torn apart as they orbited through the Milky Way's disk. Others are the remnants of dwarf galaxies, pulled apart by tidal forces as they were consumed by our larger galaxy. The halo also contains intact globular clusters, spherical collections of hundreds of thousands of stars that orbit the Milky Way as a unit. Many of these globular clusters are believed to have originally formed in smaller galaxies that were later consumed by the Milky Way. They survived the merger process because their stars are bound tightly together by gravity, unlike the more loosely organized stars of the dwarf galaxies themselves. But the feast is not over. Currently, the Milky Way is surrounded by dozens of smaller satellite galaxies. Most famous among these are the Large and Small Magellanic Clouds, visible to the naked eye from the southern hemisphere as fuzzy patches in the night sky. These two irregular dwarf galaxies contain billions of stars and are orbiting the Milky Way at distances of roughly 160,000 and 200,000 light-years, respectively. For decades, astronomers believed that the Magellanic Clouds were in stable orbits around the Milky Way, perhaps having completed many circuits in the past. But more recent measurements suggest that they may be on their first approach, having been captured by our galaxy's gravity relatively recently. Regardless of their past, their future seems clear. In billions of years, they too will likely be consumed by the Milky Way, their stars adding to our galaxy's growing collection. Other satellite galaxies include the Fornax Dwarf, the Sculptor Dwarf, the Draco Dwarf, and many others, each containing millions to billions of stars. Most of these are classified as dwarf spheroidal galaxies, small, rounded collections of old stars with little gas or dust, and thus little ongoing star formation. Many show signs of being distorted by the Milky Way's gravity, the first step in the long process of being consumed. The discovery of so many satellite galaxies and the evidence that our Milky Way has consumed others in the past raises an interesting question. Where did all these dwarf galaxies come from? The answer appears to lie in the paradigm of hierarchical galaxy formation, the idea that large structures in the universe form as smaller structures combine. In this view, the early universe was filled with small clumps of dark matter and gas that gradually came together to form the first small galaxies. These galaxies then merged to form larger ones, which merged to form even larger ones, and so on. The Milky Way and its satellites represent one such hierarchy, with our large galaxy having formed from the merger of many smaller ones, and the remaining satellites representing future additions to this growing structure. This hierarchical formation is not unique to the Milky Way. Throughout the universe, galaxies appear to form and grow through this process of merger and accretion. But studying our own galaxy gives us a front-row seat to this process, allowing us to observe the details with a precision impossible for more distant systems. The evidence of the Milky Way's cannibalistic past and present leads to an inevitable conclusion about its future. Our galaxy will continue to consume its smaller neighbors for billions of years to come. The Sagittarius Dwarf will be fully absorbed. The Magellanic Clouds will eventually spiral inward. One by one, the smaller satellites will be consumed, their stars becoming indistinguishable from the Milky Way's native population except to the most careful astronomical observations. But the Milky Way's career as a galactic cannibal may itself have an end. Our nearest large galactic neighbor, the Andromeda Galaxy, is approaching us at a speed of about 110 kilometers per second. In about 4 to 5 billion years, the Milky Way and Andromeda will begin to merge. In this encounter, our galaxy will be the consumed rather than the consumer, though the resulting galaxy, sometimes called Milkomeda, will contain stars from both original galaxies. This future merger with Andromeda is a reminder that in the cosmic ecosystem, every predator can also be prey. The hierarchy of galactic consumption continues upward, with larger and larger structures forming as time goes on. The Milky Way's hunger for smaller galaxies is just one part of this ongoing process of cosmic structure formation. The story of the Milky Way's hunger gives us a new perspective on our place in the cosmos. The stars we see in the night sky are not all native to our galaxy. Many came from other galaxies, consumed long ago by the Milky Way's gravitational forces. Our Sun, formed roughly 4.5 billion years ago from gas within the Milky Way's disk, is likely a native. But many of the stars visible to the naked eye may have originated in other galaxies, their light reaching us from across both space and time. Even some of the stars nearby might be immigrants. The Gaia-Enceladus merger happened after the Milky Way's disk had begun to form, meaning that some of its stars could have been deposited near the Sun. Every night, we might be looking at stars that formed in another galaxy, billions of years ago, now shining down on Earth as part of their new galactic home. This cosmic perspective reminds us of the impermanence of all things, even structures as vast as galaxies. The Milky Way we see today is not the same galaxy that existed billions of years ago, nor will it be the same billions of years from now. It is a dynamic, evolving structure, constantly incorporating new material and being shaped by gravitational interactions with its neighbors. In the cosmic food chain, not all galaxies are created equal. While massive spiral galaxies like our Milky Way and giant ellipticals dominate their surroundings, smaller galaxies often find themselves on the menu. These dwarf galaxies, containing anywhere from a few million to several billion stars, are the most common type of galaxy in the universe. They are also the most frequently consumed. Dwarf galaxies come in several varieties, each with distinct characteristics that tell us about their formation and evolution. Dwarf ellipticals are small, rounded galaxies containing mostly older stars with little ongoing star formation. Dwarf irregulars have no defined shape and often contain significant amounts of gas and dust, allowing them to continue forming new stars. Dwarf spheroidals are extremely low in brightness, containing primarily ancient stars and almost no gas or dust. Ultra-faint dwarfs are the smallest and dimmest of all, sometimes containing only a few thousand stars, making them difficult to detect except when they are very close to us. The local group, the collection of galaxies that includes our Milky Way and Andromeda, contains dozens of these dwarf galaxies. They orbit the larger galaxies like moths around flames, drawn in by gravity and destined, in many cases, to eventually be consumed. The Milky Way alone has at least 50 known satellite galaxies, with more being discovered as astronomical surveys become more sensitive. Most famous among the Milky Way's satellites are the large and small Magellanic Clouds, visible to the naked eye from the southern hemisphere. The Large Magellanic Cloud, at about 14,000 light-years across, contains approximately 30 billion stars. The Small Magellanic Cloud, slightly farther away, spans about 7,000 light-years and contains a few billion stars. Both are classified as dwarf irregulars, still containing significant amounts of gas and actively forming stars. For decades, astronomers believed that the Magellanic Clouds had been orbiting the Milky Way for billions of years, completing many circuits around our galaxy. However, more recent measurements of their velocities suggest they may be on their first approach, having been captured by the Milky Way's gravity only relatively recently in cosmic terms. This would explain why they still retain so much gas and are still forming stars, unlike many of the Milky Way's other satellites that have been stripped of their gas during multiple passages through our galaxy's halo. Between the Magellanic Clouds stretches the Magellanic Stream, a long trail of gas being pulled from these dwarf galaxies by the Milky Way's gravitational forces. This stream extends over 150 degrees across the sky, containing hundreds of millions of solar masses of hydrogen gas. It is a visible sign that these galaxies are already being disrupted, the first stage in what will likely be their eventual consumption by the Milky Way. The fate of the Magellanic Clouds, while still billions of years in the future, seems clear. They will continue to orbit the Milky Way, losing more and more of their gas with each passage through our galaxy's halo. Their orbits will decay due to dynamical friction, the drag effect that occurs as they move through the dark matter halo surrounding the Milky Way. Eventually, perhaps 5 billion years from now, they will merge with our galaxy, their stars becoming part of the Milky Way's disk and halo. But the Magellanic Clouds are just the largest and most visible of the Milky Way's satellites. Dozens of smaller dwarf galaxies orbit our galaxy, most of them classified as dwarf spheroidals. These include galaxies like Fornax, Sculptor, Draco, and Ursa Minor, each containing millions to hundreds of millions of stars. Unlike the Magellanic Clouds, most of these dwarf spheroidals contain very little gas and have ceased forming stars billions of years ago. The lack of gas in these dwarf spheroidals is likely due to a process called RAM pressure stripping. As these small galaxies pass through the hot, diffuse gas in the Milky Way's halo, their own gas is pushed out, much like the wind can blow the smoke away from a chimney. Without gas, star formation ceases, and the galaxies are left with only their existing stars, which gradually age and die. This is why most dwarf spheroidals contain primarily old, red stars rather than young, blue ones. In addition to losing their gas, many of these dwarf galaxies show signs of being tidally disrupted by the Milky Way's gravity. Their outer stars are being pulled away, forming streams that eventually disperse into the Milky Way's halo. The core of the dwarf galaxy may remain intact for billions of years, but its outer regions are slowly stripped away, orbit by orbit, until nothing distinct remains. One of the most dramatic examples of this process is the Sagittarius dwarf spheroidal galaxy, discovered in 1994. This galaxy is currently passing through the disk of the Milky Way, on an orbit that takes it through our galaxy approximately once every billion years. Each passage strips away more of its stars, and it has already lost a significant fraction of its original mass. The stars pulled from the Sagittarius dwarf now form a stream that completely encircles the Milky Way, a ribbon of stars wrapping around our galaxy multiple times. Some of these stars may even be passing through the solar neighborhood, visitors from another galaxy now traveling through our region of the Milky Way. In another billion years or so, the core of the Sagittarius dwarf will likely be completely disrupted, its identity lost as its stars are fully incorporated into the Milky Way. Even smaller than the dwarf spheroidals are the ultra-faint dwarf galaxies, some containing as few as 1,000 stars. These are so dim that they have only been discovered in the past 15 years or so, thanks to sensitive surveys like the Sloan Digital Sky Survey and the Dark Energy Survey. Galaxies like Segway 1, Willman 1, and Ursa Major 2 are so small and faint that they contain fewer stars than many globular clusters, raising questions about the boundary between very small galaxies and very large star clusters. These ultra-faint dwarfs are particularly vulnerable to tidal disruption by the Milky Way. Their gravity is so weak that even a distant passage near our galaxy can begin to tear them apart. Many show signs of elongation or distortion, the first hints that they are being pulled apart by tidal forces. Given their small size and the strength of the Milky Way's gravitational pull, it seems likely that many ultra-faint dwarfs have already been completely disrupted, their stars now scattered throughout our galaxy's halo. Yet for all their vulnerability, Dwarf galaxies play a crucial role in our understanding of the universe. They are thought to be the building blocks of larger galaxies, the first substantial structures to form after the Big Bang. By studying dwarf galaxies at different stages of disruption, astronomers can piece together the history of how larger galaxies like the Milky Way assembled over cosmic time. Dwarf galaxies also provide crucial insights into the nature of dark matter, the mysterious substance that makes up roughly 85% of the matter in the universe. Because they contain relatively few stars compared to their total mass, dwarf galaxies are dominated by dark matter, making them ideal laboratories for studying its properties. The way their stars move reveals the distribution of dark matter within them, while the number and properties of dwarf galaxies in the local group provide tests for different theories of what dark matter might be. Particularly interesting are the orbits of these satellite dwarf galaxies. Computer simulations based on the standard cosmological model predict that dwarf galaxies should be distributed randomly around larger host galaxies like the Milky Way. However, observations show that many of the Milky Way's satellites orbit in a thin plane, almost like the planets in our solar system. This unexpected alignment, sometimes called the vast polar structure, poses challenges for our understanding of how these dwarf galaxies formed and evolved. Similar planes of satellite galaxies have been observed around Andromeda and possibly other galaxies beyond the local group. Some astronomers suggest that these planar distributions might result from groups of dwarf galaxies falling into larger galaxies together, perhaps along cosmic filaments of dark matter. Others propose more exotic explanations, including modifications to our understanding of dark matter or gravity. The debate continues, with the dwarf galaxies themselves holding clues to these fundamental cosmic questions. The vulnerability of dwarf galaxies to consumption by their larger neighbors raises an interesting question. If this process has been going on for billions of years, why do we still see so many dwarf galaxies orbiting the Milky Way and other large galaxies? Why haven't they all been consumed already? Part of the answer lies in the orbits of these satellites. Many dwarf galaxies orbit at large distances from the Milky Way, taking billions of years to complete a single orbit. The farther a dwarf galaxy is from the Milky Way, the weaker the tidal forces it experiences, and the longer it can survive as a distinct entity. Galaxies on more elliptical orbits, which bring them closer to the Milky Way at perihelion, are more likely to be disrupted than those on more circular orbits that maintain a safer distance. Another part of the answer involves the continuous infall of new dwarf galaxies from the surrounding environment. The local group contains many dwarf galaxies that are not yet bound to either the Milky Way or Andromeda. Over time, some of these may be captured by the gravity of the larger galaxies, becoming new satellites that will eventually face the same fate as their predecessors. In this way, the population of satellite dwarf galaxies is constantly being replenished, even as individual galaxies are being consumed. The dark matter halos surrounding dwarf galaxies also play a role in their survival. Dark matter dominates the mass of dwarf galaxies, providing the gravitational glue that holds them together. The more concentrated this dark matter is toward the center of the dwarf galaxy, the more resistant it will be to tidal disruption. Galaxies with dense central dark matter concentrations can survive many close passages with the Milky Way, while those with more diffuse dark matter distributions are more easily torn apart. The interplay between these factors creates a complex ecosystem of dwarf galaxies around the Milky Way and other large galaxies. Some dwarf galaxies are relatively recent arrivals, still intact and gas-rich. Others have been orbiting for billions of years, their gas stripped away, and their outer stars drawn into streams, but their cores still intact. Still others have been completely disrupted, their stars now scattered throughout the halo of the larger galaxy, their former existence detectable only through careful studies of stellar motions and compositions. This diversity of states allows astronomers to study the process of galactic cannibalism at every stage, from the initial capture of a dwarf galaxy by a larger one, through the gradual stripping of gas and stars, to the final dissolution of the dwarf's core and the complete incorporation of its stars into the larger galaxy. It is like having a time-lapse movie of galactic evolution, with different dwarf galaxies representing different frames in the sequence. The study of dwarf galaxies and their consumption by larger galaxies also has implications for the future. The Milky Way continues to consume its smaller neighbors, growing slightly larger with each meal. But our galaxy is itself on a collision course with Andromeda, a galaxy of similar or slightly larger size. In about 4 to 5 billion years, these two spiral galaxies will begin to merge, creating an even larger elliptical galaxy that some astronomers have dubbed Milkomeda. When this merger occurs, the remaining satellite galaxies of both the Milky Way and Andromeda will find themselves orbiting the new combined galaxy. Some may be ejected into intergalactic space by the gravitational perturbations of the merger. Others may have their orbits altered, bringing them closer to the new galaxy and accelerating their eventual consumption. Still others may continue orbiting much as before, their fates delayed but not fundamentally changed. In this cosmic perspective, the consumption of dwarf galaxies by the Milky Way is just one chapter in a much longer story of galactic evolution and growth. The hierarchy continues upward, with larger structures consuming smaller ones, building ever more massive galaxies and galaxy clusters over the history of the universe. The dwarf galaxies we see today are both the building blocks from which larger galaxies were assembled and the leftovers from this ongoing process, the survivors that have not yet been fully consumed. Yet even as they are consumed, these dwarf galaxies leave their mark on their consumers. The stars they contribute carry chemical signatures that can be traced by careful spectroscopic studies. The streams they leave behind reveal the gravitational potential of the larger galaxy, allowing astronomers to map the distribution of dark matter. Their passage can trigger bursts of star formation in the larger galaxy, creating new generations of stars that would not otherwise exist. In this sense, the dwarf galaxies are not just passive victims being devoured by cosmic predators. They are active participants in an ongoing process of galactic evolution, contributing to the growth and changing structure of the larger galaxies that consume them. Their consumption is not an end, but a transformation, their stars continuing to shine as part of a new and larger cosmic entity. When galaxies collide and one begins to consume another, the process unfolds on a timescale so vast that humans could never witness it from beginning to end. A complete galactic merger might take 2 billion years or more, stretching across a period longer than the entire history of complex life on Earth. Yet by observing multiple galaxies in different stages of interaction, astronomers have pieced together the sequence of events that occurs during these cosmic feasts. It is a story of gravitational forces, transformed galaxies, new star birth, and the creation of structures that would never form in isolation. The process begins long before the galaxies physically meet. Gravity, the weakest of the fundamental forces, but the one that dominates on cosmic scales, reaches across the void between galaxies. Even at distances of millions of light years, massive galaxies can feel each other's gravitational pull. This initial attraction slowly alters their trajectories, beginning the long dance that will eventually bring them together. As the galaxies draw closer over hundreds of millions of years, their gravitational influence on each other grows stronger. The first visible signs of interaction appear in the outer regions of the galaxies, where stars and gas are less tightly bound to their galactic centers. These outer regions begin to distort, stretching toward the approaching galaxy. Astronomers call these distortions tidal tails, drawing an analogy to the tides on Earth caused by the Moon's gravity. These tidal tails can be spectacular, stretching for hundreds of thousands of light years. In some cases, they form bridges of stars and gas connecting the two approaching galaxies. In others, they sweep outward in long, curved arcs. The specific shapes depend on the relative masses of the galaxies, their orientations, and the geometry of their approach. Computer simulations can now recreate these tidal features in remarkable detail, allowing astronomers to work backward from observed distortions to understand the history of galactic encounters. The formation of tidal tails is not merely a visual phenomenon, but has profound effects on the stars within them. Stars that find themselves in these tails have been pulled away from their original orbits within their home galaxy. Some may escape entirely, flung into intergalactic space to wander between galaxies. Others will eventually fall into the larger galaxy, but on orbits very different from those they originally followed. This redistribution of stars is one of the key ways that galactic cannibalism reshapes both the consumer and the consumed. As the galaxies continue to approach, their gas clouds begin to interact. Unlike stars, which are compact objects unlikely to physically collide with one another, gas clouds are diffuse and can directly impact one another. When clouds of hydrogen gas from two different galaxies collide, they compress, increasing their density. This compression can trigger the collapse of portions of the clouds, leading to the formation of new stars. These collision-induced bursts of star formation, called starbursts, are one of the most dramatic consequences of galactic interactions. In extreme cases, the rate of star formation can increase by a factor of 10 or more compared to isolated galaxies. The new stars tend to be massive and bright, giving interacting galaxies a distinctive blue color from the light of these young, hot stars. Some of the most luminous galaxies in the universe are those undergoing major mergers with intense starbursts, shining with the light of hundreds of trillions of stars. Not all of the gas in colliding galaxies forms stars, however. Some is heated to extremely high temperatures by the energy of the collision, creating diffuse halos of hot gas that emit X-rays. Other gas may be thrown out of the galaxies entirely, forming long filaments that stretch into intergalactic space. In some cases, particularly when a smaller galaxy passes through the disk of a larger one, the gas in the smaller galaxy can be completely stripped away, halting any future star formation and leaving it with only its existing stars. The chaos of a galactic collision affects not just the stars and gas, but also the dark matter halos that surround all galaxies. Dark matter, which makes up about 85% of the matter in the universe, doesn't interact directly with normal matter except through gravity. But as the galaxies merge, their dark matter halos blend together, creating a new, combined halo. This process isn't always smooth, and simulations suggest that dark matter can form temporary shells, waves, and other structures during mergers before settling into a more uniform distribution. As the cores of the merging galaxies finally come together, several important processes occur. The most spectacular is the potential merger of the supermassive black holes that reside at the center of most galaxies. These black holes, with masses millions or billions of times that of the Sun, gradually spiral toward each other as their host galaxies merge. Eventually, they form a binary system, orbiting each other at ever-decreasing distances. In the final stages of the black hole merger, as the two massive objects orbit just a few light hours apart, they emit gravitational waves, ripples in the fabric of space-time itself. These waves carry away energy and angular momentum from the binary system, causing the black holes to spiral ever closer until they merge into a single, more massive black hole. The gravitational waves from such mergers have been detected by observatories like LIGO when they occur in distant galaxies, providing direct evidence for this aspect of galactic cannibalism. The merger of supermassive black holes can have profound effects on the surrounding galaxy. As gas falls toward the newly combined black hole, it can form an accretion disk, a swirling maelstrom of matter heated to millions of degrees before plunging beyond the event horizon. The energy released in this process can drive powerful jets of particles and radiation that extend far beyond the galaxy itself. In some cases, these jets can regulate star formation throughout the galaxy, either shutting it down by heating and dispersing gas clouds, or potentially triggering it in regions where the jets compress existing gas. Beyond the central black holes, the stars from the merging galaxies settle into new orbits around the center of the combined galaxy. This process is not instantaneous, but may continue for hundreds of millions of years after the main merger event. The resulting distribution of stars often no longer resembles either of the original galaxies, particularly in the case of major mergers between galaxies of similar mass. One of the most significant transformations that can occur during galactic cannibalism is the conversion of spiral galaxies into elliptical ones. Spiral galaxies, like the Milky Way, have a distinctive disk shape with spiral arms, a central bulge, and ordered rotational motion. Elliptical galaxies, in contrast, are more spheroidal or football-shaped, lack distinct spiral arms, and have stars moving in more random directions, rather than in a coherent rotation. When two spiral galaxies of similar mass merge, the result is almost always an elliptical galaxy. The ordered rotational motion of the original spirals is disrupted by the gravitational interactions of the merger, transformed into the random orbits characteristic of ellipticals. The gas that once fueled steady star formation in the spiral arms is either consumed in a burst of star formation during the merger, or heated and dispersed, explaining why elliptical galaxies typically have little cold gas and low rates of current star formation. This transformation from spiral to elliptical can also occur through a series of minor mergers, where a larger spiral galaxy consumes multiple smaller satellites over time. Eventually, the cumulative effect of these minor mergers can disrupt the spiral structure and transform the galaxy into an elliptical. Astronomers believe that most large elliptical galaxies observed today form through some combination of major and minor mergers over cosmic time. Not all galactic cannibalism results in elliptical galaxies, however. When a large spiral galaxy consumes a much smaller dwarf galaxy, the spiral structure may survive the encounter. The smaller galaxy's stars and gas are incorporated into the larger galaxy, but the overall dynamics of the spiral remain intact. Our own Milky Way has likely undergone several such minor mergers in its history, while maintaining its spiral structure, though its future merger with the similarly sized Andromeda galaxy will likely transform both spirals into a single elliptical. Beyond creating elliptical galaxies, galactic cannibalism can lead to a variety of other unusual structures. Some galaxies develop shells, concentric arcs of stars visible around their outskirts. These shells are thought to form when a smaller galaxy falls into a larger one on a nearly radial orbit. As the smaller galaxy passes through the center of the larger one, its stars are stripped away and spread out, eventually reaching a maximum distance from the center before falling back. This process repeats with each oscillation of the smaller galaxy's core through the larger galaxy, creating a series of shells at different radii. Other galaxies develop ring structures as a result of collision and cannibalism. The Cartwheel Galaxy is a famous example, with its distinctive wheel-like appearance resulting from a smaller galaxy having plunged through its center. The collision sent a wave of compressed gas outward from the center, triggering star formation in a perfect ring around the original galaxy. Similar ring galaxies have been observed elsewhere in the universe, each telling the story of a cosmic collision. Even more exotic are polar ring galaxies, where a ring of stars, gas, and dust orbits perpendicular to the main disk of a spiral galaxy. These are thought to form when a larger galaxy strips material from a smaller one passing on an orbit perpendicular to the larger galaxy's disk. The stripped material settles into a stable orbit around the larger galaxy, forming the polar ring. These structures could not form in isolation and are a direct consequence of galactic cannibalism. The consumption of one galaxy by another also affects the stellar populations of both galaxies. The stars in different galaxies can have different chemical compositions depending on the history of star formation and element production in each galaxy. When galaxies merge, these distinct stellar populations mix together, creating a combined galaxy with a more diverse set of stars than either original galaxy had on its own. Astronomers can detect this mixing by studying the metallicity of stars, a term that refers to the abundance of elements heavier than hydrogen and helium. Stars with low metallicity formed early in the universe's history, before many generations of previous stars had enriched the interstellar medium with heavier elements. stars with high metallicity formed more recently from gas that had been enriched by multiple previous generations of stars. When a larger galaxy consumes a smaller one, the smaller galaxy often contributes stars with lower metallicity than the average for the larger galaxy. By mapping the metallicity of stars throughout a galaxy, astronomers can identify regions where stars from consumed galaxies predominate. In the Milky Way, for example, many of the low metallicity stars in the halo are thought to have originated in smaller galaxies consumed by our own. The merging of galaxies also affects the overall age distribution of stars in the resulting galaxy. The starburst triggered by a major merger creates a distinct population of stars all formed at approximately the same time. Billions of years later, astronomers can identify this population as a spike in the age distribution, a record of the merger event long after other signs have faded away. Indeed, the evidence of past galactic feasts can persist for billions of years after the event itself is over. Long after tidal tails have dissipated and gas clouds have settled, the orbits and chemical compositions of stars retain the memory of their origins. By studying these subtle clues, astronomers can reconstruct the cannibalistic history of galaxies that now appear serene and isolated. This archaeological approach to galactic history has been particularly fruitful in studying our own Milky Way. By mapping the positions, motions, and chemical compositions of millions of stars, astronomers have identified the remnants of multiple galaxies consumed by the Milky Way over its long history. Each one has left its mark, contributing to the complex structure of our galactic home. The process of galactic cannibalism also provides insights into the formation and evolution of galaxies more generally. The hierarchical model of galaxy formation suggests that all large galaxies have grown through a series of mergers with smaller ones, with the rate of major mergers decreasing over cosmic time as the universe expands and galaxies move farther apart on average. This model makes specific predictions about the frequency and characteristics of galaxy mergers at different epochs in the universe's history. By observing galaxies at different redshifts, corresponding to different times in the past, astronomers can test these predictions. Generally, the observations support the hierarchical model, showing a higher rate of major mergers in the early universe and the gradual assembly of larger galaxies through both major and minor mergers over cosmic time. The role of galactic cannibalism in galaxy evolution also depends on the environment. Galaxies in dense clusters experience more frequent interactions and mergers than those in more isolated regions. This environmental dependence helps explain why elliptical galaxies, which often form from mergers, are more common in dense clusters, while spiral galaxies are more prevalent in less dense regions where major mergers are less frequent. The evidence of past and ongoing galactic cannibalism surrounds us, from the stellar streams in the Milky Way's halo to the distorted shapes of interacting galaxies visible through telescopes. Far from being an exotic or rare phenomenon, the consumption of one galaxy by another appears to be a fundamental process in the evolution of the universe, building larger structures from smaller ones over billions of years. And yet, despite the violence implied by terms like cannibalism and consumption, the process is in many ways creative rather than destructive. Stars are rarely destroyed in these encounters. Rather, they find new orbits and new galactic homes. Gas clouds collide and compress, triggering the birth of stars that would not otherwise exist. Black holes merge, sending gravitational waves rippling through space-time. The result is not just the growth of galaxies, but their transformation into new forms with new properties, contributing to the rich diversity of galaxies we observe in the universe today. On a clear, dark night, away from city lights, a faint smudge of light is visible to the naked eye in the constellation Andromeda. This unassuming patch of luminosity is the Andromeda Galaxy, also known as Messier 31, the closest major galaxy to our Milky Way. At a distance of about 2.5 million light-years, Andromeda appears peaceful and distant, a neighbor we observe from afar. But this tranquility is deceptive. Andromeda is not just a passive observer of our cosmic neighborhood. It is a giant in waiting, a galaxy on a collision course with our own. The realization that Andromeda is moving toward the Milky Way came in 1912, when astronomer Vesto Slipher measured its radial velocity, the component of its motion directed toward or away from us. Most galaxies show a redshift, indicating they are moving away from us due to the expansion of the universe. Andromeda, however, shows a blue shift, meaning it is moving toward us at a speed of about 110 kilometers per second. This approaching motion was a curiosity for decades, but its full implications were not understood until relatively recently. In 2012, astronomers using the Hubble Space Telescope made precise measurements of Andromeda's proper motion. That is, its movement across the sky perpendicular to our line of sight. Combined with the radial velocity measurements, these observations provided a complete three-dimensional trajectory for Andromeda relative to the Milky Way. The results were striking. Not only is Andromeda approaching us, but it is on a direct collision course with the Milky Way. In approximately 4.5 billion years, the two galaxies will begin to merge, initiating a cosmic dance that will transform both galaxies and the space around them. This future collision is not a remote possibility, but a virtually certain fate for both galaxies. The merger will unfold over billions of years, with several close passages before the galaxies finally coalesce. The first approach will dramatically distort both galaxies, drawing out long tidal tails of stars and gas. Stars in the outer regions of both galaxies will be flung into wide orbits, creating a diffuse halo around the merging pair. Some stars may be ejected into intergalactic space, doomed to wander the void between galaxies. As the galaxies pass through each other, their gas clouds will collide, triggering bursts of star formation. These starbursts will create millions of new stars, many of them massive and bright, briefly illuminating the collision with the blue light of young stellar populations. The supermassive black holes at the centers of both galaxies will begin their own gravitational dance, eventually spiraling toward each other and merging into a single more massive black hole. After several passes over the course of 1 billion years or more, the two galaxies will settle into a single combined structure. The ordered spiral patterns of both the Milky Way and Andromeda will have been disrupted, replaced by a more random distribution of stars, characteristic of elliptical galaxies. The result will be a giant elliptical galaxy, sometimes dubbed Milkomeda, containing the stars, gas, dust, and dark matter of both original galaxies. The collision of the Milky Way and Andromeda will reshape our local cosmic neighborhood. The numerous satellite galaxies that currently orbit both the Milky Way and Andromeda will find themselves in new orbits around the combined galaxy. Some may be pulled inward by the changing gravitational field, accelerating their own eventual consumption. Others may be ejected outward, potentially escaping the gravitational pull of Milkomeda entirely. For all the drama of this future collision, it is important to understand what it does not mean. Despite the term collision, individual stars are extremely unlikely to physically impact one another. The vast distances between stars mean that even as the galaxies pass through each other, the stars themselves will simply move past one another, their orbits altered by gravitational interactions rather than direct collisions. Similarly, our solar system is not in immediate danger from this event. While the Sun and planets will likely be moved to a different location within the merged galaxy, the chances of another star passing close enough to disrupt the solar system are extremely small. The Earth will face more immediate threats from the Sun's own evolution, which will enter its red giant phase around the same time the galactic merger begins, making our planet uninhabitable long before any effects from the Andromeda collision would reach us. Astronomers have created detailed simulations of the future merger, allowing us to visualize how it might appear from different perspectives. From Earth's vantage point, assuming human eyes were still around to see it, Andromeda would grow larger and larger in the night sky as it approaches. Eventually, it would stretch across the entire sky, no longer a distant smudge, but a vast structure completely surrounding us. As the first close passage occurs, both galaxies would be severely distorted, with stars streaming away in all directions. The night sky would be transformed, filled with new patterns of stars entirely different from the constellations familiar to us today. The Milky Way's band across the sky would be disrupted, replaced by a more chaotic distribution covering much more of the celestial sphere. During the most active phases of the merger, the rate of star formation would increase dramatically. This would make the combined galaxy temporarily brighter and bluer, potentially visible across much greater cosmic distances than either galaxy is today. After the merger is complete and star formation subsides, the resulting elliptical galaxy would be redder and somewhat less luminous, though still one of the largest galaxies in our local cosmic neighborhood. These simulations are not mere speculation, but are based on observations of similar mergers occurring elsewhere in the universe. By studying galaxies in various stages of collision and merging, astronomers have built up a detailed understanding of how these processes unfold. The future merger of the Milky Way and Andromeda is expected to follow patterns observed in countless other galactic collisions throughout cosmic history. The approaching Andromeda galaxy is more than just a future threat to the Milky Way's separate existence. It is a complex and fascinating object in its own right, with a history of galactic cannibalism that rivals or exceeds our own galaxies. Understanding Andromeda provides insights into the Milky Way's future and offers a comparative case study in galactic evolution. Andromeda is a spiral galaxy somewhat larger than the Milky Way, with a diameter of about 220,000 light-years, compared to the Milky Way's 100,000 light-years. It contains roughly 1 trillion stars, about twice the number in our galaxy. Like the Milky Way, it has a supermassive black hole at its center, though Andromeda's central black hole is larger, with a mass about 100 million times that of the Sun. The structure of Andromeda includes a substantial disk with well-defined spiral arms, a central bulge of older stars, and an extensive halo reaching far beyond the visible disk. Recent observations have revealed that Andromeda's disk is thicker than previously thought and may have been puffed up by past mergers with smaller galaxies. Its halo contains numerous globular clusters and shows evidence of several generations of past galactic cannibalism. Andromeda's history as a galactic cannibal has been revealed through detailed observations of its stellar populations. Its halo contains streams and shells of stars that could not have formed with the main galaxy, but must have been added through the accretion of smaller galaxies. The chemical composition of these stars differs from that of stars formed within Andromeda itself, providing further evidence of their external origin. One of the most striking pieces of evidence for Andromeda's cannibalistic past is the giant stellar stream, a long trail of stars extending from the galaxy's halo. This stream, discovered in 2001, stretches more than 6 degrees across the sky, corresponding to at least 160,000 light-years in physical length. It appears to be the remains of a dwarf galaxy that came too close to Andromeda and was torn apart by tidal forces, its stars now scattered along its former orbit. Further observations have revealed additional stellar streams and shells around Andromeda, each representing the remnants of a different consumed galaxy. These structures tell the story of Andromeda's growth through multiple acts of galactic cannibalism stretching back billions of years. Like the Milky Way, Andromeda has been growing by consuming its smaller neighbors throughout its history. Andromeda's current satellites include at least 28 known dwarf galaxies, the most prominent being M32, a compact elliptical galaxy that appears to have been severely stripped of its outer stars by Andromeda's tidal forces. The distribution of these satellites is not random, but shows alignment in a thin plane similar to the plane of satellites observed around the Milky Way. This unexpected structure poses challenges for our understanding of how these satellite systems formed. The similarities between Andromeda and the Milky Way make their future collision a fascinating case study in galactic evolution. Both are large spiral galaxies with supermassive black holes, extensive halos, and numerous satellite galaxies. Both have grown through the consumption of smaller galaxies and continue to do so today. Their merger will be less the meeting of strangers than the reunification of distant relatives. Galaxies that formed in the same local environment and have evolved along parallel paths. Yet, there are also significant differences between the two galaxies. Andromeda is larger and more massive, containing roughly twice as many stars as the Milky Way. Its spiral structure shows evidence of a more violent merger history, with a more extended and disturbed disk. The supermassive black hole at its center is more massive and may have been more active in the past. These differences will influence how the merger unfolds and the precise nature of the resulting combined galaxy. The approaching Andromeda represents a shift in the Milky Way's role in the cosmic hierarchy. Throughout much of its history, our galaxy has been the consumer rather than the consumed, growing by absorbing smaller galaxies rather than being absorbed. The merger with Andromeda will be a more equal encounter, with neither galaxy clearly dominating the other, though Andromeda's greater mass gives it a slight advantage. This change in roles is reflective of the broader hierarchical structure of galaxy formation and evolution. Throughout the universe, smaller structures merge to form larger ones, which in turn merge to form even larger ones. The Milky Way's consumption of dwarf galaxies, Andromeda's similar history, and their future merger with each other are all part of this ongoing process of hierarchical growth. The merger of the Milky Way and Andromeda will not be the end of this process, but rather the beginning of a new phase. The resulting elliptical galaxy will likely continue to grow by absorbing remaining dwarf galaxies in the local group. On even longer timescales, it may participate in further mergers with other large galaxies in neighboring groups, building even larger structures as the universe continues to evolve. There is evidence that this future major merger has been preceded by smaller interactions between the Milky Way and Andromeda. The vast halos of both galaxies, extending hundreds of thousands of light years beyond their visible disks, may already be overlapping and interacting in subtle ways. Stars and gas at these extreme distances feel the gravitational pull of both galaxies, beginning the long process of redistribution that will eventually encompass all the stars in both galaxies. Observations of the space between the Milky Way and Andromeda have revealed a tenuous bridge of hydrogen gas that may connect the two galaxies. This structure, known as the Magellanic Stream, was once thought to be solely related to the Milky Way's interaction with the Magellanic Clouds. But some astronomers now suggest it may be influenced by Andromeda's gravity as well. If confirmed, this would be the first direct evidence that the two galaxies are already beginning to interact across the vast distance that separates them. As astronomers continue to map the motions of stars and gas in and around both galaxies, our understanding of their past interactions and future collision becomes increasingly detailed. Each new observation refines the predicted trajectory of Andromeda and the timeline of the merger. While the broad outlines have been established, many details remain to be filled in, from the precise path Andromeda will take to the specific effects the collision will have on different regions of both galaxies. The approaching Andromeda also raises questions about the fate of the supermassive black holes at the centers of both galaxies. These black holes, with masses millions or billions of times that of the Sun, are key components of most large galaxies. When galaxies merge, their central black holes eventually find each other through a process called dynamical friction, gradually spiraling inward until they form a binary system. The final merger of these black holes would release enormous energy in the form of gravitational waves, ripples in space-time that travel at the speed of light. While this event would not be directly harmful to stars or planets in the merged galaxy, it would represent one of the most energetic events in the history of the local group. Future gravitational wave observatories might be able to detect similar black hole mergers in distant galaxies, providing insights into the process that will eventually occur in our own cosmic neighborhood. Beyond the two supermassive black holes at the centers of the Milky Way and Andromeda, both galaxies likely contain thousands of smaller black holes distributed throughout their disks and halos. These too will eventually find themselves in the merged galaxy, continuing their lives as invisible gravitational engines occasionally revealed when they interact with nearby stars or gas clouds. The merger of the Milky Way and Andromeda will also affect the other members of the local group, the collection of more than 50 galaxies to which both belong. The third largest galaxy in the local group, the Triangulum Galaxy, or M33, may eventually join the merger, creating an even larger combined galaxy. Alternatively, it might be ejected to a more distant orbit by the gravitational perturbations of the Milky Way-Andromeda merger. The numerous dwarf galaxies that orbit both the Milky Way and Andromeda will find their orbits altered by the changing gravitational field. Some may be pulled inward, accelerating their eventual consumption. Others may be pushed outward, gaining energy from the merger through a gravitational slingshot effect similar to that used by spacecraft to gain speed from planetary flybys. The final distribution of satellite galaxies around the merged Milkomeda will depend on the precise details of the merger process, which can only be approximated by current simulations. For all the attention paid to the Milky Way-Andromeda merger, it is worth noting that such events are common throughout the universe. Astronomers have observed thousands of interacting and merging galaxies, from pairs just beginning their gravitational dance to fully merged systems still showing the scars of their violent pasts. The future collision of the Milky Way and Andromeda is not exceptional, except in its proximity to us and the fact that it involves our home galaxy. This commonality of galactic mergers places the approaching Andromeda in a broader cosmic context. It is not an anomaly or a catastrophe, but a normal part of galactic evolution, a process that has been occurring since the first galaxies formed and will continue for billions of years to come. The collision that will end the separate existence of the Milky Way is not the end of a story, but the beginning of a new chapter in the ongoing narrative of cosmic structure formation. As we contemplate this future collision, we are reminded of the dynamic nature of the universe. Galaxies are not static collections of stars, but evolving systems, growing, changing, and sometimes merging over timescales far beyond human experience. The apparently unchanging night sky is, on cosmic timescales, a constantly shifting landscape of stars, gas, and galaxies, all moving under the inexorable pull of gravity. The cosmic phenomenon of galactic cannibalism raises a fundamental question. Why do galaxies consume one another? Is this process merely an accident of cosmic geography? Galaxies happening to cross paths in the vastness of space? Or is there a deeper pattern at work? A cosmic imperative that drives galaxies to merge and grow over time. To understand why galaxies eat each other, we must explore both the mechanisms that bring galaxies together and the role these mergers play in the evolution of the universe. At the most basic level, galaxies consume one another because of gravity. Every mass in the universe attracts every other mass, from the smallest particles to the largest structures. Galaxies, as collections of hundreds of billions of stars plus gas, dust, and dark matter, exert enormous gravitational pulls. When two galaxies pass close enough to one another, this mutual gravitational attraction can overcome the galaxy's independent motions, binding them together in an orbital dance that eventually leads to merger. But this explanation, while technically accurate, is incomplete. It tells us how galaxies come together, but not why this process is so common, or what role it plays in the broader story of cosmic evolution. For a deeper understanding, we need to consider the context in which galaxies form and evolve, reaching back to the earliest moments of the universe. According to the standard cosmological model, the universe began with the Big Bang, approximately 13.8 billion years ago. In its earliest moments, the universe was incredibly hot and dense, a plasma of elementary particles with no distinct structures. As it expanded and cooled, small fluctuations in density, quantum fluctuations magnified by a period of rapid expansion called inflation, became the seeds of future structure. Under the influence of gravity, regions of slightly higher density began to attract surrounding matter, growing denser still. This process was greatly enhanced by dark matter, the mysterious substance that makes up about 85% of the matter in the universe. Dark matter interacts only through gravity, allowing it to begin clumping together while normal matter was still too hot and energetic to form stable structures. These dark matter clumps formed a cosmic web, with denser regions connected by filaments and separated by vast voids. As the universe continued to cool, normal matter, primarily hydrogen and helium gas, fell into the gravitational wells created by the dark matter. In the densest regions, this gas became concentrated enough to begin forming stars, the first galaxies emerging roughly 200 to 500 million years after the Big Bang. These early galaxies were small by modern standards, containing perhaps millions or billions of stars, rather than the hundreds of billions found in large galaxies today. They were also irregular in shape, lacking the ordered spiral or elliptical structures that characterize many contemporary galaxies. Rich in gas, but relatively poor in elements heavier than helium, these first galaxies were sites of vigorous star formation, but had chemical compositions very different from those we observe today. From the beginning, these early galaxies were not isolated. Formed along the same filaments of the cosmic web, they were born into gravitationally bound groups and clusters. Even as they were still assembling from the primordial gas, they were already beginning to interact with one another, setting the stage for billions of years of mergers and acquisitions. The hierarchical model of galaxy formation suggests that larger structures form as smaller ones merge together. The smallest dark matter halos, containing perhaps only enough gas to form a globular cluster of stars, combine to form dwarf galaxies. These dwarf galaxies merge to form larger ones, which in turn combine to create the massive galaxies we see today. Each step in this hierarchy involved the gravitational interaction of existing structures, the larger consuming the smaller in a cosmic food chain. This hierarchical assembly was particularly active in the early universe, with galaxies closer together in the smaller, denser cosmos, and with more gas available for star formation. The rate of both galaxy formation and galaxy mergers was much higher than we observe today. The first few billion years after the Big Bang saw a frenzy of galactic cannibalism that built up the first large galaxies and began to establish the structure of the cosmic web we observe in the present day. As the universe expanded and the average distance between galaxies increased, the rate of major mergers, those between galaxies of similar mass, decreased. However, the process never ceased entirely. Galaxies that had formed in the same general region of the cosmic web remained gravitationally bound to one another, orbiting around common centers of mass. Within these bound groups and clusters, galaxies continued to interact and occasionally merge, though at a lower rate than in the early universe. This ongoing process of mergers and acquisitions serves several vital functions in galactic evolution. Most fundamentally, it builds larger structures from smaller ones, allowing the formation of the massive galaxies that serve as the gravitational anchors of the cosmic web. Without galactic cannibalism, the universe would contain only dwarf galaxies, lacking the diversity of structures we observe today. Beyond simply creating larger galaxies, the merger process reshapes galaxies in ways that would not occur through internal evolution alone. When galaxies collide, the gravitational interactions can transform spiral galaxies into ellipticals, create bars and rings within galaxies, and trigger bursts of star formation that would not otherwise occur. These changes in structure and stellar population contribute to the rich diversity of galaxies observed in the modern universe. Mergers also play a crucial role in the growth and activation of supermassive black holes at the centers of galaxies. These black holes, with masses millions or billions of times that of the Sun, are found at the heart of virtually every large galaxy. When galaxies merge, their central black holes eventually find each other and merge as well, creating even more massive black holes. During galaxy mergers, significant amounts of gas can be driven toward the center of the merging system. Some of this gas may fall into the central black hole or holes, creating an accretion disk that heats up and emits enormous amounts of energy. This process can create active galactic nuclei, some of the most luminous objects in the universe, capable of outshining all the stars in their host galaxy combined. The energy released by active galactic nuclei can have profound effects on their host galaxies. Radiation and particle jets can heat and disperse gas throughout the galaxy, potentially shutting down star formation by preventing gas from cooling and collapsing to form new stars. This process, called active galactic nucleus feedback, is thought to play a key role in regulating star formation in massive galaxies, and may explain why we observe fewer very massive galaxies than cosmological models would predict without such feedback. Galactic cannibalism also affects the chemical composition of galaxies. Elements heavier than hydrogen and helium, collectively referred to as metals in astronomical terminology, are produced primarily in stars and dispersed when those stars explode as supernovae. Over time, successive generations of stars enrich the interstellar medium with these heavier elements, changing the composition of gas available for future star formation. Different galaxies may have different chemical enrichment histories depending on their star formation rates, the distribution of stellar masses within them, and their ability to retain the metals produced by their stars rather than losing them to intergalactic space through supernova-driven outflows. When galaxies merge, these different chemical signatures mix together, creating a more complex chemical structure than either galaxy had before. This chemical mixing is particularly important in the growth of larger galaxies. Massive elliptical galaxies, many of which are thought to have formed through multiple mergers, often show evidence of complex chemical evolution that cannot be explained by a simple, isolated star formation history. The diversity of stellar populations within them, with different ages and chemical compositions, tells the story of multiple merged galaxies, each bringing its own unique chemical signature to the combined system. Galactic cannibalism can also trigger starbursts, periods of intense star formation far above the galaxy's normal rate. When gas-rich galaxies collide, their gas clouds can be compressed by the gravitational interactions, creating the dense conditions necessary for rapid star formation. These starbursts can momentarily increase a galaxy's star formation rate by factors of 10 or more, creating large populations of stars all at approximately the same time. These starburst events are particularly important in the formation of elliptical galaxies. Unlike spiral galaxies, which typically form stars continuously at a moderate rate, ellipticals appear to have formed most of their stars in intense bursts long ago, with little star formation occurring in the present day. The merger of gas-rich spirals with the attendant starbursts can produce exactly this pattern, converting the galaxy's gas into stars during the merger and leaving the resulting elliptical with little gas for ongoing star formation. The importance of galactic cannibalism varies with galaxy mass. The smallest dwarf galaxies may evolve primarily through internal processes, with mergers playing a relatively minor role. But for larger galaxies, particularly those with masses similar to or greater than the Milky Way, external interactions and mergers are fundamental to their evolution. At the extreme end of the mass spectrum, the largest galaxies in the universe, giant ellipticals found at the centers of galaxy clusters, appear to have grown primarily through cannibalism. These monsters, containing trillions of stars, have consumed dozens or even hundreds of smaller galaxies over their lives. Their enormous sizes, diffuse stellar halos, and multiple nuclei all tell the story of repeated mergers throughout their history. The environment in which a galaxy exists also influences the importance of cannibalism in its evolution. Galaxies in dense clusters experience more frequent interactions and mergers than those in more isolated regions of the cosmic web. This environmental dependence helps explain why elliptical galaxies, which often form from mergers, are more common in dense clusters, while spiral galaxies are more prevalent in less dense regions where major mergers are less frequent. The role of mergers in galaxy evolution also changes over cosmic time. In the early universe, mergers were more frequent and played a crucial role in building up the first massive galaxies. In the present-day universe, mergers are less common but still occur, particularly within gravitationally bound groups and clusters. In the far future, as the universe continues to expand, and the average distance between galaxies increases, mergers will become increasingly rare, except within these bound structures. This changing merger rate is reflected in the changing appearance of galaxies throughout cosmic history. Observations of distant galaxies, which due to the finite speed of light show us the universe as it was in the past, reveal a higher fraction of irregular and disturbed galaxies compared to the present day. These irregularities are often the result of mergers and interactions, supporting the hierarchical model in which larger galaxies assemble from smaller ones over cosmic time. The study of why galaxies eat each other also has implications for our understanding of the Milky Way's past and future. Our galaxy has clearly participated in galactic cannibalism, consuming smaller galaxies throughout its history and incorporating their stars into its disk and halo. This process continues today, with galaxies like the Sagittarius dwarf being actively disrupted by the Milky Way's gravitational forces. In the future, the Milky Way itself will be consumed, or at least transformed, through its merger with Andromeda. This event, predicted to begin in about 4.5 billion years, will convert both spiral galaxies into a single, larger elliptical. The resulting galaxy will then likely continue to grow by consuming the remaining smaller galaxies in the local group, a process that will unfold over many billions of years. This future merger is not a random accident, but a direct consequence of the gravitational interactions that bind together the local group. The Milky Way and Andromeda, as the two largest galaxies in the group, were always likely to eventually merge due to their mutual gravitational attraction. The specific timing and trajectory of the merger depend on the precise distribution of mass within the local group, including the contributions of dark matter halos that extend far beyond the visible portions of the galaxies. The inevitability of the Milky Way-Andromeda merger highlights a key aspect of why galaxies eat each other. Within gravitationally bound structures like groups and clusters, mergers are not rare accidents but expected outcomes of the ongoing gravitational interactions between galaxies. Given enough time, a significant fraction of the galaxies in any bound group will eventually merge, driven by the same force, gravity, that initially brought them together. This pattern of merger and growth is fundamental to the evolution of the universe as a whole. The cosmic web we observe today, with its clusters, filaments, and voids, is the product of billions of years of gravitational attraction, condensing matter into increasingly concentrated structures separated by ever emptier voids. Galactic cannibalism is one manifestation of this broader process, building larger stellar systems just as gravity builds larger structures at all scales. In this context, the consumption of one galaxy by another is not a cosmic accident or aberration, but a normal and necessary part of how the universe evolves. It is through these mergers that the diversity of galactic structures we observe came to be, from the smallest dwarf irregulars to the largest ellipticals. Without galactic cannibalism, the universe would be a far more uniform and less interesting place, populated only by small, isolated galaxies, rather than the rich hierarchy of structures we see today. The study of why galaxies eat each other thus leads us to a deeper understanding of the fundamental forces shaping the universe. It is not merely a story of individual galaxies growing larger, but of the universe itself, evolving, organizing matter into ever more complex structures across billions of years of cosmic time. Galactic cannibalism is both a builder of galaxies and a shaper of the cosmos, a process as fundamental to the universe as the birth and death of stars. And so, when we look out at distant galaxies caught in the act of merging, their shapes distorted by gravitational tides and their gas ignited in bursts of new star formation, we are not seeing cosmic violence, but cosmic creation. These merging galaxies are not being destroyed, but transformed, their separate identities giving way to a new, combined entity that carries forward elements of both precursors while being something entirely new. In this way, galactic cannibalism embodies the creative potential of gravity, building new structures from old in the never-ending evolution of the cosmos. I'll now continue with Chapter 7, aiming for approximately 13,500 characters. Chapter 7. Observing the feasts across the universe. As we've explored the process and importance of galactic cannibalism, a question naturally arises. How do astronomers actually observe these cosmic feasts? Given that galaxy mergers unfold over billions of years, far longer than human civilization has existed, how can we study a process that exceeds our lifetimes by factors of millions? The answer lies in the vastness of the universe itself, which provides us with countless examples of merging galaxies at every stage of the process, from initial approach to final coalescence. The most direct observations of galactic cannibalism come from telescopes capable of seeing distant galaxies in detail. The Hubble Space Telescope, launched in 1990, revolutionized our view of interacting galaxies, providing unprecedented clarity and resolution that cut through the blurring effects of Earth's atmosphere. Its successor, the James Webb Space Telescope, launched in 2021, extends these capabilities further with its larger mirror and ability to observe in infrared wavelengths, allowing it to see through dust clouds that often obscure the most active regions of merging galaxies. These telescopes, along with ground-based observatories equipped with adaptive optics to compensate for atmospheric distortion, have revealed a zoo of interacting galaxies throughout the universe. Some are just beginning their gravitational dance, their shapes only slightly distorted as they make their first approach. Others are in the midst of collision, their structures severely disrupted, and their gas clouds compressed into bursts of new star formation. Still others show the aftermath of merger, their shapes settled but bearing telltale signs of their violent past. Among the most famous examples of galaxies caught in the act of merging are the antennae galaxies, also known as NGC 4038 and NGC 4039. Located about 65 million light-years from Earth, these two spiral galaxies are in the midst of a collision that began approximately 500 million years ago. The most striking feature of the system is the pair of long tidal tails extending from the galaxies, giving them an appearance reminiscent of insect antennae, hence their name. The antennae provide a preview of what might occur when the Milky Way and Andromeda begin their own merger billions of years from now. Like our galaxy and its neighbor, the original galaxies in the antennae system were both spiral galaxies of roughly similar size. Their collision has distorted their spiral structures, flinging stars and gas into the long tidal tails, while compressing other gas clouds to trigger intense star formation in their overlapping regions. Observations of the antennae across the electromagnetic spectrum reveal different aspects of the merger. Visible light shows the distribution of stars, including the dramatic tidal tails. Infrared observations penetrate the dust clouds to reveal hidden regions of star formation. X-ray observations show hot gas heated by the collision, while radio wavelengths trace the distribution of cold hydrogen gas that will fuel future star formation. Together, these multi-wavelength observations provide a comprehensive view of the physical processes occurring in this cosmic collision. Another dramatic example is the system known as the Mice Galaxies, or NGC 4676. This pair of spiral galaxies, located about 300 million light-years from Earth, are in an earlier stage of interaction than the antennae. They have made one close pass by each other, but have not yet begun to merge. The gravitational interaction during this flyby has drawn out long tidal tails from both galaxies, giving them the appearance of mice with long tails, earning them their nickname. The mice are particularly valuable for testing computer simulations of galaxy interactions. Because they are at a relatively early stage of merging, with their original spiral structures still largely intact, they provide a clear example of how tidal forces distort galaxies during their initial encounters. By comparing observations of the mice with simulations of galaxy interactions, astronomers can refine their models and improve their ability to predict how such mergers evolve over time. One of the most striking examples of a minor merger, in which a large galaxy consumes a much smaller one, is the Tadpole Galaxy, or UGC 10214. Located about 400 million light-years from Earth, this system consists of a spiral galaxy with an enormously long tidal tail, stretching over 150,000 light-years. This tail was created when a smaller galaxy passed close to the spiral, its gravitational pull drawing out stars and gas from the larger galaxy's disk before continuing on its way. The tadpole illustrates how even a relatively brief encounter between galaxies can have dramatic and long-lasting effects on their structure. The smaller galaxy, although not captured by the larger one in this case, nevertheless transformed it, creating a distinctive feature that will persist for hundreds of millions of years. Similar processes may have occurred in the Milky Way's past, creating streams and tails that astronomers are only now beginning to map in detail. Perhaps the most famous interacting system of all is not a merger in progress, but a future one. The Whirlpool Galaxy, or M51, and its companion NGC 5195, located about 23 million light-years from Earth, are often featured in astronomical photographs due to their striking appearance. The larger spiral galaxy, M51, is currently being distorted by the gravitational pull of the smaller NGC 5195, which appears to be moving around it. This system provides a snapshot of the early stages of a minor merger, with the smaller galaxy already beginning to be disrupted by tidal forces, while the larger galaxy's spiral structure is being enhanced by the gravitational interaction. Over the course of hundreds of millions of years, the smaller galaxy is likely to be fully incorporated into the larger one, its stars adding to the spiral's disk and halo, while its gas fuels new star formation. Beyond these well-known examples, astronomers have catalogued thousands of interacting and merging galaxies throughout the observable universe. The Atlas of Peculiar Galaxies, compiled by Holton Arp in the 1960s, was an early attempt to systematically document galaxies with unusual shapes, many of which are now recognized as systems in various stages of interaction and merger. More recent surveys, using automated analysis of millions of galaxy images, have identified vast numbers of merging systems, allowing statistical studies of how merger rates vary with cosmic time, galaxy mass, and environment. These observations confirm key aspects of the hierarchical model of galaxy formation. They show that mergers were more common in the early universe, when galaxies were closer together in the smaller, denser cosmos. They demonstrate that environment matters, with mergers more frequent in dense galaxy groups and clusters compared to more isolated regions. And they reveal that the outcomes of mergers depend on the properties of the merging galaxies, such as their mass ratio, gas content, and orbital parameters. Beyond simply identifying merging systems, modern observations allow astronomers to study the physical processes occurring within them in unprecedented detail. Spectroscopy, the analysis of light broken down into its component wavelengths, reveals the composition, temperature, and motion of gas in these systems. By mapping how the spectral lines of various elements shift due to the Doppler effect, astronomers can create detailed maps of how gas is moving within merging galaxies, tracing the complex flows driven by gravitational interactions. These observations show that mergers drive gas toward the centers of galaxies, where it can fuel bursts of star formation and feed supermassive black holes. They reveal shock fronts where gas clouds collide at high speeds, compressing the gas and triggering the formation of massive star clusters. And they demonstrate how some gas can be ejected from the merging system entirely, enriching the intergalactic medium with elements produced in the galaxy's stars. Advanced observational techniques also allow astronomers to study the stellar populations within merging galaxies. By analyzing the combined light from millions of stars, they can determine the ages and chemical compositions of different regions within these systems. These studies reveal the history of star formation within the galaxies, showing how mergers trigger bursts of new star birth while redistributing existing stellar populations. In recent years, observations have extended beyond the visible structure of merging galaxies to include their dark matter halos. While dark matter cannot be directly observed, its gravitational effects on visible matter can be detected through techniques such as gravitational lensing, where the dark matter's gravity bends light from more distant objects. These observations confirm that when galaxies merge, their dark matter halos combine as well, gradually relaxing into a new combined structure that encompasses the merged galaxy. The study of merging galaxies is not limited to optical telescopes. Radio observatories such as the Very Large Array and ALMA, the Atacama Large Millimeter Array, map the cold gas within these systems, showing how it is compressed and heated during collisions. X-ray telescopes like Chandra and XMM Newton reveal hot gas and active galactic nuclei, while infrared observatories like Spitzer and now the James Webb Space Telescope penetrate dust clouds to reveal hidden regions of star formation. This multi-wavelength approach provides a comprehensive view of merging galaxies impossible to obtain from any single type of observation. The combined data reveal the complex interplay of stars, gas, dust, and dark matter during these cosmic collisions, allowing astronomers to build increasingly sophisticated models of how galaxies grow and evolve through cannibalism. The most distant merging galaxies observed to date are seen as they were when the universe was less than 1 billion years old, just a fraction of its current age of 13.8 billion years. These early systems are typically smaller and more irregular than modern galaxies, consistent with the hierarchical model in which large galaxies assemble from smaller ones over cosmic time. By observing galaxies across a range of distances, and thus across different epochs in cosmic history, astronomers can trace how the merger process and its outcomes have evolved over billions of years. This historical perspective is complemented by detailed observations of nearby merging systems, where the higher resolution available allows astronomers to study the process in much greater detail. Systems like the Antennae galaxies, at 65 million light-years, can be observed down to the scale of individual star clusters, revealing how merger-induced star formation proceeds on scales from tens to thousands of light-years. Even closer interactions, such as the ongoing disruption of dwarf galaxies within the local group, can be studied star by star, providing insights into the smallest scales of the cannibalism process. The culmination of these observations is a comprehensive picture of how galaxies grow through mergers across cosmic time. From the assembly of the first galaxies in the early universe to the ongoing consumption of dwarf galaxies by larger ones in the present day, astronomers can now trace the entire history of galactic cannibalism. This picture confirms the fundamental role of mergers in building the diversity of galaxies we observe, from the smallest dwarfs to the largest ellipticals. Observations of merging galaxies also provide a window into the future of our own Milky Way. By studying systems similar to the future Milky Way Andromeda merger, astronomers can make increasingly detailed predictions about how that event will unfold. Computer simulations, calibrated against observations of actual merging systems, allow visualizations of what the night sky might look like from Earth as Andromeda approaches, if humanity or its descendants are still around to witness it. The James Webb Space Telescope, with its unprecedented sensitivity and resolution in the infrared, is expected to revolutionize our understanding of galaxy mergers further. Its ability to penetrate dust clouds will reveal the most active regions of star formation within merging galaxies, while its sensitivity will allow it to detect fainter features such as tidal streams and shells around galaxies that have undergone past mergers. Already, in its first year of operation, it has provided stunning new images of interacting galaxies, revealing details never before seen. Future observatories, both space-based and on the ground, will continue to advance our ability to observe galactic cannibalism in action. The Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2020s, will survey vast areas of the sky with Hubble-like resolution, potentially discovering many new examples of interacting galaxies. Extremely large ground-based telescopes with mirrors 30 or 40 meters in diameter will provide unprecedented resolution for detailed studies of these systems. Beyond new observatories, advances in computational power and algorithms are enhancing our ability to analyze existing observations. Machine learning techniques can now automatically identify interacting galaxies in survey data, while sophisticated simulations can predict the complex gas dynamics and star formation processes that occur during mergers. These computational tools, combined with new observations, are driving rapid progress in our understanding of how galaxies grow through cannibalism. One of the most exciting areas of current research is the connection between galaxy mergers and gravitational waves. When galaxies merge, their central supermassive black holes eventually coalesce as well, generating powerful gravitational waves in the process. While current gravitational wave detectors like LIGO are not sensitive to the low-frequency waves produced by merging supermassive black holes, future observatories such as LISA, the Laser Interferometer Space Antenna, will be able to detect them. The combination of electromagnetic observations of merging galaxies with gravitational wave detections of their merging black holes will provide a multi-messenger view of the cannibalism process, unprecedented in astronomy. The gravitational waves will reveal the masses and spins of the merging black holes, while electromagnetic observations will show the surrounding galaxy and any associated flares of light as the black holes merge. Together, these observations will test our understanding of how supermassive black holes grow alongside their host galaxies. As our ability to observe galactic cannibalism across cosmic time continues to improve, we gain an ever clearer picture of our place in the evolving universe. The Milky Way, for all its apparent stability over human history, is revealed as a dynamic system that has grown through the consumption of smaller galaxies and will one day be consumed itself in a merger with Andromeda. The stars we see in the night sky, rather than being fixed and eternal, are participants in a cosmic dance of merging galaxies that has been ongoing for billions of years and will continue for billions more. This perspective transforms our understanding of the cosmos from a static, unchanging backdrop to human affairs into a dynamic, evolving stage on which the drama of galaxy formation and evolution plays out. The observations of merging galaxies across the universe show us both our past, in the hierarchical assembly of the Milky Way from smaller precursors, and our future in the approaching collision with Andromeda. They connect our local cosmic neighborhood to the broader universe, revealing the common processes that shape galaxies throughout cosmic time. When a smaller galaxy is consumed by a larger one, what happens to its stars, its gas, its very essence? Is it truly destroyed, erased from the cosmic ledger, or does something of it persist? The process of galactic cannibalism, for all its apparent violence, is not one of annihilation, but of transformation and preservation. The consumed galaxy is not erased, but absorbed, its components redistributed, and its memory preserved in subtle but detectable ways within the larger galaxy that consumed it. To understand what it means for a galaxy to be eaten, we must first recognize that galaxies are not solid objects, but vast collections of stars, gas, dust, and dark matter, all bound together by gravity. When one galaxy consumes another, these components are not destroyed, but redistributed. Stars from the consumed galaxy continue to shine, but now they orbit within the gravitational field of the larger galaxy. Gas and dust mix with the larger galaxy's interstellar medium, potentially forming new stars that bear the chemical signature of their origin. Even the dark matter from the consumed galaxy continues to exist, contributing to the larger galaxy's gravitational field. The clearest evidence that consumed galaxies are remembered comes from stellar streams, those ribbons of stars observed around galaxies like the Milky Way. Each stream represents the remnants of a dwarf galaxy or globular cluster that has been torn apart by tidal forces. The stars in these streams still move together, following similar orbits that trace their common origin. By mapping these streams, astronomers can identify the remains of dozens of smaller galaxies that have been consumed by our Milky Way over its long history. These stellar streams persist for billions of years, long after the original galaxy has lost its distinct identity. The stars within them have been freed from their original galaxy's gravitational bind, but they remain connected through their similar velocities and orbits. In a real sense, the consumed galaxy lives on in these streams, its memory preserved in the correlated motions of its former stars. Beyond visible streams, the memory of consumed galaxies is also preserved in the chemical compositions of their stars. Stars form from gas clouds that contain particular mixtures of elements, reflecting the history of star formation and supernova explosions that came before them. Dwarf galaxies, with their different star formation histories and abilities to retain metals from supernovae, often develop distinctive chemical signatures that differentiate them from larger galaxies like the Milky Way. When these dwarf galaxies are consumed, their stars bring these distinctive chemical signatures with them. By analyzing the chemical compositions of stars in our galaxy, astronomers can identify groups that originated in the same dwarf galaxy, even if those stars are now scattered across different regions of the Milky Way. These chemical tags provide another way to trace the ghosts of galaxies long since consumed. A particularly powerful example comes from the Gaia-Enceladus merger, a significant event in the Milky Way's past where it consumed a dwarf galaxy with a mass perhaps 10% of its own. Stars from this consumed galaxy have distinctive chemical compositions and orbital characteristics that allow them to be identified even billions of years after the merger. Through detailed surveys of stellar motions and compositions, astronomers have reconstructed the rough size and properties of this long-gone galaxy, remembering an entity that ceased to exist as a distinct object billions of years ago. The process of consumption also leaves physical structures within the larger galaxy that serve as memorials to its past meals. Shells of stars, concentric arcs visible around some elliptical galaxies, form when a smaller galaxy on a nearly radial orbit is disrupted, its stars spreading out and then clustering at the apocenters of their new orbits. These shells can persist for billions of years, visible reminders of a merger long after other signs have faded. Similarly, rings of stars or gas can form when a smaller galaxy passes through a larger one in a particular orientation. The Cartwheel Galaxy, with its distinctive ring shape, was created when a smaller galaxy plunged through the center of a larger one, creating a ripple-like wave of star formation that expanded outward. This structure, which will persist for hundreds of millions of years, stands as a monument to the smaller galaxy that created it, even though that galaxy itself may no longer exist as a distinct entity. Even the central bulges of spiral galaxies may, in many cases, be memorials to past mergers. The stars in these bulges often have different ages and chemical compositions from those in the disk, suggesting they formed earlier or under different conditions. Some astronomers propose that the bulges of galaxies like the Milky Way were formed or enhanced by the accretion of dwarf galaxies early in their history. If so, then the very shape of our galaxy carries the memory of those long-ago feasts. The supermassive black holes at the centers of most large galaxies also serve as records of past consumption. These black holes grow partially through mergers with the black holes from consumed galaxies. While the details of the precursor black holes are lost once they merge, the increased mass of the combined black hole preserves the fact that a merger occurred. By studying the masses of supermassive black holes and their relationship to their host galaxy's properties, astronomers can infer aspects of the galaxy's merger histories. Yet perhaps the most profound form of remembrance comes through star formation triggered by galactic cannibalism. When galaxies merge, the compression of gas clouds can lead to bursts of star formation that would not have occurred otherwise. These new stars, formed from the mixed gas of both galaxies, represent a new generation born directly from the merger process. These stars carry the combined chemical signatures of both parent galaxies, a literal blending of their gaseous content. They are neither fully of the consuming galaxy nor fully of the consumed, but something new that emerged from the interaction of both. In this way, consumed galaxies are not just remembered passively, but contribute actively to the creation of new stellar populations that would not exist without them. The stars formed during merger-induced starbursts can be identified long after the merger itself has concluded. By analyzing the ages of stars throughout a galaxy, Astronomers can identify cohorts that all formed at approximately the same time, often corresponding to periods of interaction and merger. These age spikes in the stellar population serve as timestamps of past cannibalism events, allowing the reconstruction of a galaxy's merger history from the stars themselves. Beyond new stars, mergers can also trigger the formation of globular clusters, dense collections of hundreds of thousands of stars bound together by gravity. Some of the globular clusters observed around large galaxies today may have formed during ancient merger events, while others may have been brought in as part of consumed dwarf galaxies. Either way, these clusters persist for billions of years, serving as some of the longest-lived monuments to the process of galactic consumption. The impact of consumed galaxies extends beyond their direct contributions of stars and gas. The gravitational interactions during mergers can induce changes in the structure of the larger galaxy, creating features such as bars, rings, and warps that would not form through internal processes alone. These structural changes can alter the evolution of the galaxy for billions of years, affecting everything from its rate of star formation to the orbits of its globular clusters and satellite galaxies. In a real sense, then, every large galaxy we observe today is a composite entity, the accumulated product of numerous acts of cannibalism stretching back across cosmic time. The Milky Way is not just the Milky Way, but also contains the ghosts of Gaia Enceladus, the Sagittarius Dwarf, and dozens of other consumed galaxies whose names we may never know. Each has left its mark, contributing stars, gas, and structural features that make our galaxy what it is today. This perspective transforms our understanding of galactic identity. A galaxy is not a fixed, unchanging entity, but a dynamic system that grows and evolves through the incorporation of smaller systems. The boundaries between one galaxy and another become blurred in this view, with stars that originated in a consumed dwarf galaxy now fully part of the larger galaxy that consumed it. The identity of a galaxy, like that of a living organism, encompasses both what it began as and what it has incorporated over its long history. The parallels to biological systems are striking. Just as multicellular organisms grow by consuming other organisms and incorporating their nutrients, galaxies grow by consuming smaller galaxies and incorporating their stars and gas. In both cases, the consumed entity is not destroyed, but transformed, its components repurposed within the larger system. The memory of what was consumed persists, although in altered form. This biological metaphor extends further when we consider the role of mergers in diversifying galactic populations. Just as genetic exchange between organisms can lead to greater diversity within a species, the exchange of stars and gas between merging galaxies leads to greater diversity in the combined galaxy. Stars with different ages, chemical compositions, and orbital characteristics mix together, creating a richer, more complex system than either galaxy had been on its own. The process of being eaten thus takes on a different meaning in the galactic context. Rather than ending the existence of the consumed galaxy, it extends and transforms that existence. The stars of the smaller galaxy continue to shine, now as part of a larger cosmic entity. Its gas may form new stars that would never have existed if the galaxy had remained isolated. Even its identity persists, detectable in the streams, chemical signatures, and structural features it leaves behind. This is not to deny the violence of the consumption process. The smaller galaxy is certainly disrupted, its structure torn apart by tidal forces, and its gas heated and compressed by the collision. Individual stars may be flung into new orbits, far from their original compatriots, or in rare cases even ejected from the combined galaxy entirely. The coherent entity that was the original galaxy ceases to exist as such. Yet, this disruption is not the end of the story, but the beginning of a new chapter. The dispersed stars of the consumed galaxy become part of a larger narrative, contributors to the continuing evolution of the combined galaxy. They are not lost or forgotten, but integrated, their light continuing to shine, and their motion continuing to influence the dynamics of their new galactic home. In some cases, the memory of the consumed galaxy is preserved quite literally in the night sky as seen from Earth. Some of the stars visible to the naked eye may have originated in dwarf galaxies consumed by the Milky Way billions of years ago. When we look up at these stars, we are seeing the light from another galaxy now incorporated into our own, a direct connection to a cosmic entity long since transformed through cannibalism. The fate of the Milky Way itself, which will eventually be consumed in a merger with Andromeda, can be understood in this same framework. Our galaxy will lose its distinct spiral structure and separate identity, becoming part of the new elliptical galaxy, sometimes called Milkomeda. Yet the stars of the Milky Way will continue to shine, now orbiting within this larger structure. The memory of our galaxy will persist in the distribution, motions, and chemical compositions of these stars, detectable to any astronomers that might study them billions of years in the future. This perspective offers a kind of cosmic immortality. Galaxies, like the stars they contain, have finite lives as distinct entities. Yet just as the elements forged in dying stars are incorporated into new generations of stars and planets, the components of consumed galaxies are incorporated into larger galaxies that continue to evolve. Nothing is truly lost in this process, only transformed and integrated into more complex cosmic structures. The record of past galactic feasts is written in the stars themselves, in their positions, motions, ages, and chemical compositions. By reading this record, astronomers can reconstruct the history of galaxy assembly across cosmic time, from the first small galaxies forming after the Big Bang to the massive ellipticals observed today. Each large galaxy contains within it the echoes of all the smaller galaxies it has consumed, preserved in subtle but detectable ways. This cosmic memory extends beyond individual galaxies to the largest structures in the universe. Galaxy clusters, collections of hundreds or thousands of galaxies bound together by gravity, also grow through a process of hierarchical assembly, with smaller groups joining together to form larger clusters. The distribution of galaxies within a cluster, the hot gas between them, and the dark matter halo surrounding them all preserve the memory of this assembly history. Even on the largest scales, the cosmic web itself, with its filaments, sheets, and voids, represents the accumulated history of gravitational interactions, stretching back to the earliest moments after the Big Bang. The memory of the universe is not stored in some external record, but is intrinsic to its structure, readable from the distribution of matter across all scales from individual stars to the cosmos as a whole. In this cosmic context, the consumption of one galaxy by another takes on a different significance. It is not a random act of destruction, but a necessary step in the hierarchical assembly of structure in the universe. The consumed galaxy is not ended, but transformed, its components incorporated into a larger cosmic entity that carries forward its legacy. The memory of what was consumed persists, encoded in the very fabric of the consuming galaxy. This process of consumption and remembrance has been occurring since the first galaxies formed, building ever larger structures from smaller ones. It will continue for billions of years to come, as the remaining small galaxies are absorbed by larger ones, and some large galaxies merge with each other. In the far future, as the universe continues to expand and the average distance between galaxy groups increases, this process will slow but never entirely cease within gravitationally bound structures. The legacy of consumed galaxies thus stretches forward to the end of the universe itself. The stars they contributed, the structural changes they induced, and the new star formation they triggered all become part of the ongoing cosmic narrative. In a universe that feeds itself, nothing is truly lost, only transformed, its memory preserved in the evolving structures that continue its legacy. Galactic cannibalism may sound violent, the stuff of cosmic catastrophe and destruction, but in space, it is the rhythm of growth, a slow dance, a long embrace, a quiet assimilation. What appears destructive on human timescales is, in cosmic terms, simply transformative, the way the universe builds ever larger structures from smaller ones. As we've journeyed through the dark between the stars, we've witnessed galaxies in various stages of consumption. Some, like our Milky Way, actively devouring smaller neighbors such as the Sagittarius dwarf. Others, like the Antennae galaxies, locked in mutual consumption, their spiral arms distorted into long tidal tails as they merge into something new. Still others, giant ellipticals at the centers of galaxy clusters, the products of dozens or even hundreds of past mergers, their forms bearing the accumulated history of countless cosmic meals. These acts of galactic cannibalism are not rare aberrations, but fundamental aspects of how the universe evolves. From the smallest dwarf galaxies to the largest superclusters, structures grow through hierarchical assembly, smaller units combining to form larger ones. The consumption of one galaxy by another is just one manifestation of this broader process, the universe feeding on itself to build ever more complex structures. What makes this process remarkable is not the disappearance of the consumed galaxies, but their preservation. The stars of a devoured dwarf galaxy continue to shine, now orbiting within the halo of the larger galaxy that consumed it. Their distinctive chemical compositions and correlated motions tell the story of their origin, a memory of a separate galactic identity, now transformed but not erased. The gas from consumed galaxies may form new stars, creating populations that would not have existed if the galaxies had remained separate. The merging of supermassive black holes at their centers sends gravitational waves rippling through the fabric of space-time, a signal of cosmic restructuring detectable across billions of light years. Even the dark matter, halos of consumed galaxies persist, their mass now contributing to the gravitational field of the combined galaxy. The galaxies that shine brightest in our telescopes, those massive ellipticals and giant spirals that dominate their local environments, may have been built from dozens of smaller galaxies over cosmic time. Their current forms and structures are the accumulated product of every merger they have experienced, every smaller galaxy they have consumed. They are not just single entities, but composite systems, galactic collages assembled over billions of years. Our own Milky Way, that band of light stretched across the night sky, is no exception. The stars above our heads include natives formed within the main body of our galaxy, but also immigrants that originated in other galaxies long since consumed. The halo of the Milky Way, that sparse region of stars surrounding the main disk, is largely composed of stars stripped from smaller galaxies over the course of billions of years. And the feast continues. The Sagittarius dwarf spheroidal galaxy is currently passing through the disk of the Milky Way, its stars being gradually stripped away and incorporated into our galaxy. The large and small Magellanic Clouds, visible as fuzzy patches in the southern sky, will likely be consumed billions of years from now. And most dramatically, the Andromeda Galaxy is approaching, destined to merge with the Milky Way in about 4.5 billion years. This future merger with Andromeda reminds us that in the cosmic food chain, every predator can also be prey. The Milky Way, having consumed numerous smaller galaxies throughout its history, will itself be consumed, or at least transformed, in this coming collision. The resulting galaxy, sometimes called Milkomeda, will be an elliptical rather than a spiral, containing the combined stars of both original galaxies, but with a very different structure. Yet even in this transformation, the essence of the Milky Way will persist. Its stars will continue to shine, now orbiting within the new elliptical galaxy. Its chemical signature will be detectable in those stars, a record of its separate history before the merger. The streams and shells of stars from galaxies it consumed will become part of the new combined system, memories of memories in the layered history of galactic assembly. This perspective gives us a new way to think about permanence and impermanence in the cosmos. Galaxies, like the stars they contain, have finite lives as distinct entities. Yet just as the elements forged in dying stars are incorporated into new generations of stars and planets, the components of consumed galaxies are incorporated into larger galaxies that continue to evolve. Nothing is truly lost in this process, only transformed and integrated into more complex cosmic structures. So as you drift towards sleep beneath the stars, remember that some of the points of light you see were born in galaxies long since devoured by our own. The atoms in your body, forged in stars that may have belonged to different galaxies before being consumed by the Milky Way, connect you directly to this ongoing process of cosmic rearrangement. You are made of star stuff, as Carl Sagan famously noted, but that star stuff itself carries the memory of multiple galactic homes. In a universe that feeds itself, building larger structures from smaller ones across billions of years, nothing is truly lost, only transformed. The light from distant galaxies caught in the act of merging brings us images from different epochs in this ongoing process. A cosmic time-lapse showing the slow assembly of structure from the first small galaxies to the giants we see today. And still, the process continues, following the same fundamental force, gravity, that has shaped the universe since its earliest moments. The same physics that draws a falling apple toward Earth also draws galaxies together across millions of light years, orchestrating a cosmic dance of consumption and growth that has been ongoing for nearly 14 billion years and will continue for billions more. The story of galactic cannibalism is thus not one of cosmic violence, but of cosmic creation. Not the end of something, but the beginning of something new. Not a story of loss, but one of transformation and preservation. In a universe built through hierarchical assembly, every structure contains within it the memory of all that came before, a nested history of consumption and growth written in the stars themselves. So sleep beneath the stars, some of which were born from galaxies long since devoured. In a universe that feeds itself, nothing is truly lost, only transformed.